Hello dear students, welcome to mathematics class. So in the last class we have discussed necessary condition and sufficient condition for the function to be analytic. And in this class let us discuss examples on that analytic function or how to prove that a function is analytic. So by using the necessary condition that if a function is analytic then CR equations are satisfied, or if CR equations are satisfied then the function is analytic. So here show that W is equal to Z plus e power Z is analytic, and hence find dW by dZ or f dash of Z. So while deriving the necessary condition we came across that f dash of Z. So f dash of Z is given by dou u by dou x plus I into dou v by dou x, that is the formula already used in the necessary and sufficient condition, and also we know that how it came, that f dash of Z. And now we need to show that this function, that Z plus e power Z is analytic. So analytic means the equation has to satisfy the CR equations. So already we know what are CR equations. The CR equations are given by dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to dou v by dou x. Those four equations are called as CR equation, and those four are nothing but the partial derivatives of the function u and v with respect to x and y. Means while proving the analytic function, the function must be of the form f of z is equal to u plus iv, means where u and v are the functions of x and y, because we are considering partial derivatives with respect to x and y, not with respect to z. So therefore first of all we need to express the function in terms of x and y, though that is similar to the previous examples, that examples on functions of a complex variable. By putting z equal to x plus iy, we have separated real and imaginary parts of the function. So similarly here first we need to express the function as real and imaginary parts separately. So now let us consider that w is nothing but f of z. So here given that f of z equal to z plus e power z, right. So now z plus e power z is equal to f of z, then put z equal to x plus iy. So by substituting z equal to x plus iy, we can express the function as u of x comma y plus I into v of x comma y. So therefore f of z equal to x plus iy plus e power x plus iy, then it is equal to x plus iy as it is plus e power x into e power iy by using the law of indices. Then this is x plus iy plus e power x into. So by using the de Moivre's theorem, e power I theta is cos theta plus I sin theta. So here e power iy is cos y plus I sin y, then it is equal to x plus iy plus e power x cos y plus I into e power x sin y. Then collecting the terms which are multiplied by I and not multiplied by I. So then it is x plus e power x cos y plus I into y plus e power x sin y is equal to f of z, it is equal to u plus iv. So now it implies that u is equal to x plus e power x cos y and v is equal to y plus e power x sin y. Now we got real and imaginary parts, where u is real part and v is imaginary part. So now we need to find all the four partial derivatives. So first dou u by dou x. So whenever we are differentiating partially with respect to one variable, then the remaining variable will act as a constant. So, here we have two variables x and y, but here x is a variable and e power x is a function of x, hence it is variable, and cos y is constant. So, therefore, if we differentiate with respect to x, that cos y will not change because that is the constant. So, then dou u by dou x is equal to 1 plus e power x cos y, because the differentiation of x is 1 and differentiation of e power x is e power x itself. So, therefore, it is 1 plus e power x cos y. Then dou u by dou y with respect to y if you differentiate. Now, x is constant, hence its differentiation is 0 plus e power x as it is, then differentiation of cos y is minus sin y, hence it is minus e power x sin y is equal to dou u by dou y, and dou v by dou x. So, dou v by dou x is y is constant with respect to x, so hence its derivative is 0 plus e power x differentiation is e power x only, then sin y is constant. So, therefore, it is e power x sin y, and dou v by dou y. So, dou v by dou y means y plus e power x sin y is equal to v. Now, differentiate v with respect to y, treating x as constant. So, now differentiation of y with respect to y is 1 plus e power x is constant as it is, then differentiation of sin y is cos y. Now, by observing these 4 partial derivatives, we can write the conclusion as, now dou u by dou x is 1 plus e power x cos y, and dou v by dou y is also 1 plus e power x cos y. So, hence dou u by dou x equal to dou v by dou y, and the second CR equation is dou u by dou y is equal to minus dou v by dou x. So, here dou u by dou y is minus e power x sin y and dou v by dou x is e power x sin y. Means if you multiply this with negative sign, then that becomes dou u by dou y is equal to minus dou v by dou x. So, therefore, dou u by dou y is equal to minus dou v by dou x. So, it implies that CR equations, the Cauchy-Riemann equations satisfied. So, if these equations satisfied, then we can say that f of z is analytic. So, this is the way to prove the function f of z is analytic or not. So, here w is equal to z plus e power z. First, we need to express that as e power x, sorry, the f of z equal to u plus iv, where u is real part of the function and v is the imaginary part of the function. Then consider the 4 partial derivatives, the dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. Then by using or by comparing those 4 derivatives, we can come at the conclusion that dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. So, here these two must be of opposite sign. If one is positive, the other must be negative. Then if these two conditions are holds good, then CR equations satisfied. If CR equation satisfied, then we can conclude that f of z is analytic. Then we need to prove f dash of we need to find f dash of z. So, here we know that f dash of z equal to, we know that f dash of z equal to dou u by dou x plus I into dou v by dou x. So, it is f dash of z. Now, this is equal to, now substitute the values of dou u by dou x and dou v by dou x. Dou u by dou x is 1 plus e power x cos y plus I into e power x sin y. Then here we are finding f dash of z, means the result of that function should be a function of z. So, therefore, we need to simplify this in such a way that that should be a function of z. Now, this is 1 plus e power x cos y plus I into e power x sin y. So, it is 1 plus. In these two functions we can consider e power x as common, then remaining cos y plus I sin y, and 1 plus e power x, here cos y plus I sin y can be written as e power I y by using de Moivre's theorem. Then it is 1 plus e power x plus I y, and we know that x plus I y equal to z. So, therefore, it is 1 plus e power z is equal to f dash of z. So, it is compulsory that f dash of z must be a function of z, means while finding the analytic or while proving the analytic function, we are using x plus I y is equal to or z equal to x plus I y. But here while finding f dash of z, it is in reverse order, means we need to substitute x plus I y equal to z, hence we will get the derivative of f of z as a function of z. The next example is, show that f of z equal to sin z is analytic and find f dash of z. So, it is also similar to the previous example, only the function is different, that f of z equal to sin z. So, first express this f of z equal to sin z as f of z equal to u plus iv. Now, f of z equal to sin z, then f of z equal to sin of x plus iy, because that z equal to x plus iy. Now, sin of a plus b, the expansion of sin of a plus b is sin a cos b plus cos a sin b. So, then it is sin x cos iy plus cos x sin iy, then it is sin x. So, here cos iy and sin iy. So, already we know what are hyperbolic functions. So, by the properties of those functions, that cos iy can be written as cos hyperbolic y and sin iy can be written as I into sin hyperbolic y. So, these two are the important results, cos iy equal to cos hyperbolic y, sin iy is equal to I sin hyperbolic y, then it is cos hyperbolic y plus, here sin iy is I into sin hyperbolic y. So, therefore, here I am writing I here into cos x sin hyperbolic y, which is equal to f of z. So, now it implies that u equal to sin x cos hyperbolic y and v is equal to cos x sin hyperbolic y, because real and imaginary parts of that function. Then use the partial differentiation now, then dou u by dou x. So, here differentiation of sin x is cos x and cos hyperbolic y as it is, and dou u by dou y, here sin x as it is, and differentiation of cos hyperbolic y is sin hyperbolic y. Then dou v by dou x. So, dou v by dou x is differentiation of cos x, that is minus sin x sin hyperbolic y as it is, and dou v by dou y is equal to cos x as it is, differentiation of sin hyperbolic y is cos hyperbolic y. Now, here dou u by dou x, dou v by dou y, then dou u by dou y, dou v by dou x. The magnitudes are same, but here these two are of opposite sign. Then it implies that dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. It implies CR equations satisfied, and f of z is analytic. Next we need to find f dash of z. So here f dash of z equal to dou u by dou x plus I into dou v by dou x. So here this is important formula that you have to remember this one, f dash of z equal to dou u by dou x plus I into dou v by dou x. Now dou u by dou x is cos x cos hyperbolic y plus I into dou v by dou x, that is minus sin x sin hyperbolic y. Now cos x, now use the properties again, cos hyperbolic y and I sin hyperbolic y in reverse order. So cos hyperbolic y is what? Cos iy, here minus is there, that becomes minus, here I am writing sin x and I into sin hyperbolic y. This is equal to cos x cos iy minus sin x I sin hyperbolic y. So I sin hyperbolic y is equal to sin iy. So it is sin iy. Now it is of the form cos a cos b minus sin a sin b, which can be written as cos of x plus iy, which is equal to cos z, that is f dash of z. So here we have proved that the function is analytic and we have determined that f dash of z. So here it is given that f of z equal to sin z, and this that we can directly differentiate the function f of z with respect to z. But here we cannot differentiate that z because z is a function of two variables. Hence we have to use the formula that f dash of z equal to dou u by dou x plus I into dou v by dou x, because we are writing that f of z equal to u plus iv. It is not a function of z directly, right? So there, that's why we are using the formula here, but the answer will be same. If the differentiation of f of z is f dash of z, which is equal to cos z, but that is not the way to prove or finding f dash of z. Whenever the question is asked to find f dash of z, we need to use the formula dou u by dou x plus I into dou v by dou x. It is because the function f of z is a function of two variables u and v, and again u and v are the functions of x and y. So therefore we cannot differentiate directly that f of z. The next example is, show that f of z equal to log z, where z is not equal to 0, is analytic, and find f dash of z. So now let us express that f of z is equal to u plus iv. Now f of z equal to log z, then f of z equal to log of x plus iy. So in B.Sc first semester we have logarithm of a complex number. So by using that concept, we are writing this log of x plus iy as 1 by 2 log of x square plus y square plus I into tan inverse of y by x. So it is the formula for logarithm of a complex number, 1 by 2 log of x square plus y square plus I into tan inverse of y by x, where x is real part and y is imaginary part of that complex number x plus iy. So, therefore, u is equal to 1 by 2 log of x square plus y square, and v is equal to tan inverse of y by x. Then dou u by dou x, 1 by 2 constant, then log f of x, that is 1 divided by x square plus y square into f dash of x is 2x, and 2 get cancelled, it is x divided by x square plus y square, that is dou u by dou x. Then dou u by dou y, again it is 1 by 2, 1 divided by x square plus y square into 2y. So, 2 get cancelled, it is y divided by x square plus y square. Then dou v by dou x and dou v by dou y. Now, dou v by dou x. So, the differentiation of tan inverse of x is 1 divided by 1 plus x square, hence it is 1 divided by 1 plus y square by x square into, again differentiation of y by x is minus y divided by x square, because the differentiation of 1 by x is minus 1 by x square and y is constant as it is. Then on simplifying this one, we get x square divided by x square plus y square minus y divided by x square. So, x square get cancelled, it is equal to minus y divided by x square plus y square, and dou v by dou y. So, again tan inverse of y by x. So, tan inverse of y by x is 1 divided by 1 plus y square by x square into, now differentiation of y by x is 1 by x, because differentiation of y is 1, that x is constant, that becomes 1 by x. Then it is equal to x square divided by x square plus y square into 1 by x. So, here x and x get cancelled, remaining x divided by x square plus y square. Now, here dou u by dou x equal to x by x square plus y square, and dou v by dou y is same, and dou u by dou y is y by x square plus y square, and dou v by dou x is minus y by x square plus y square. So, therefore, dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Hence, CR equations satisfied and function f of z is analytic. Then we need to find f dash of z. So, now f dash of z is equal to dou u by dou x plus I into dou v by dou x. So, here we know that dou u by dou x is x divided by x square plus y square plus I into dou v by dou x is minus y divided by x square plus y square. Then by taking the LCM here, x square plus y square is LCM, then we can write this as x minus iy divided by x square plus y square. Then x minus iy divided by. So, here x square plus y square can be written as x plus iy into x minus iy, because a plus ib into a minus ib is equal to a square plus b square. So, here x minus iy get cancelled, it is 1 divided by x plus iy, hence it is equal to 1 by z, that is f dash of z. So, it is the way to find the first order derivative of the function f of z. So, these are the important examples of that analytic function and finding the derivative of the function.